Okay, welcome back, everyone. Our next session is from Maria Patterson, who's an astronomer at UW. Who's going to be telling us about building a community fountain. Take it away.
Okay, so this talk is going to be all about streaming data technologies. So I'm going to talk a little bit about Kafka and Spark and Avro. Is anyone familiar with Kafka in this room? I just wanted to get a show of hands. Oh, great. There's some Kafka users here. I'm going to talk about it in the context of building an astronomical data stream. This is public data. It's really exciting. It's coming out of the University of Washington. And what we're trying to do is we're trying to build an ecosystem that is friendly enough so that anyone can kind of jump in and take a little bit of the astronomy data stream and build some apps and tools and whatever they think is really cool and inspiring. And so I just have a few pictures here of one of my favorite fountains. This is from Chicago, so I just moved to Seattle recently from Chicago, of Crown Fountain. And Crown Fountain is in Chicago in Millennium Park, and it's one of these fountains that's been sort of lauded for its universal design in that it has it's built up this community around it of people who go just as tourists. You have kids that are playing the fountain. It's got this like big black granite reflecting pool and these two towers, and the towers show these faces of different community members. And at nighttime, it's all lit up, and people take really great pictures around it. And so it's got this beautiful universal design element delivering up this fountain, this stream of water. And so we're trying to do the same sort of thing, but with an astronomical data stream. And so this is just in the inside Crown Fountain. It does look really simple on the outside. And you think, oh, these are just two towers. But when you look at it in a little more detail, it's really complex and sort of the architecture behind it, because you're putting all these lights and this system in with this water streaming in. And so this is the south tower of Crown Fountain in detail, and some of the lighting system beneath there that I just wanted to show up because I love Chicago. So just a quick blurb about me. I am now a scientist at the University of Washington. Before that, I worked way back when I got my PhD in astronomy, and I worked on star formation in outer disks. So there's a link to my thesis if you're really interested. I think no one has read my thesis, not even me, so don't bother. But after that, I worked a lot in cloud computing at the University of Chicago, where I did some reanalysis pipelines using Storm and Hadoop and Accumulo for NASA satellite imagery analysis. And this system with Storm and Hadoop and Accumulo was just so hard to do reanalysis of data that was streaming in. And so when I moved to learning about Kafka and Spark together, this has kind of really reoriented me into a much more user-friendly system that I'm glad to talk to you about today. I also worked a little bit on NOAA's move to the cloud. So a few years ago with the Obama administration, there was a big emphasis on having data that was open gov, open data, and making everything machine readable, open to the public. And so I worked a little bit on the NOAA Big Data project when they were trying to move about a petabyte of data to start out with, of climate data and weather data, meteorological data, into the different cloud systems. Amazon, Google, IBM, Microsoft, and something called the Open Commons Consortium, which is a consortium of academic institutions and universities and research labs that work together to try and get data publicly available and with services on top in such a way that you can analyze data and move it around. We want the data to be portable, so you're not, kind of stuck in one environment or another. You can really move it into a cloud. You can move it out to your laptop. You can move it wherever you need to move it. And I did work a little bit on some API-based data services around something called the Open Science Data Cloud when I was at the University of Chicago, which was a petabyte scale system where we provided a pool of data on different kinds of medical data, genomics data, weather data, the satellite data, natural language processing data, all kinds of data. And we developed API-based data services so you could grab that data and you could find what you need and you could pull it to some, basically like Elastic Cloud, virtual machines, and do your analysis right there in our petabyte scale cloud. And so there's a great paper that we wrote about this system, which we call a data commons system. It's called A Case for Data Commons Towards Data Science as a Service, and that was published last year in a special issue on computing for data science and engineering. A little more about me, blah, blah, blah. I'm a Cleveland native, so I like the Cavs, but I'm a Chicago transplant, so I love the Cubs. I also, I have my main Twitter running on the bottom footer here on my slides, but I also tweet my runs. If you're a distance runner, I run on Run Average. I love eating pizza, old-fashioned donuts, and old-fashioned drinks, and beer. And recently, if you saw the movie Hidden Figures, I was awarded, I'm a hidden figure, guys. I'm actually a hidden figure from Pepsi's Hidden Figure contest. And you can watch my little video about what STEM means to me as an underrepresented woman in STEM on my website. The video is actually hidden for some reason on YouTube, so it's kind of funny that that happened. But you can find it on my website there. Okay, so this is a slide that talks about streaming technologies over the past 20 years. And so I'm starting off here in 1997. In August 1997, this is when Netflix started. So remember Netflix when it was only by mail? So you had to pick out what you wanted to watch like a week in advance, which is hilarious now because I remember there were times when I would order a DVD from Netflix and then I would order the same DVD like a month later on accident because I forgot that I already watched that DVD. Anyway, so 20 years ago, that was what Netflix was like. And then in the year 2000, Roy Fielding defined REST in his thesis. REST standing for Representational State Transfer, I think that's what it stands for. And then after that, things sort of exploded in the past 20 years. And so on the bottom, I have the founding of all these different companies that use a lot of these streaming technologies that I'm going to be talking about. So LinkedIn in 2002, Facebook in 2004, YouTube 2005, Google had chat in 2005, Twitter and AWS in 2006, Hadoop started out in 2006 also, GitHub in 2008, WhatsApp 2009, Pinterest in 2010, Instagram also in 2010, and Snapchat in 2011. And so that covers a lot of the ones that I use. I think there's more. My little brothers would put more stuff from 2012 to 2017, but these are the main ones that I use here. And so what these companies have in common is that they're using a lot of the streaming big data tech. And also another thing that they have in common is that they all contribute to open source. So you can find a GitHub for each of these companies online with a lot of open source tools around big data streaming technologies. And so what we're trying to do in the astronomical community, where I do most of my work, is contribute to open source and to use a lot of the big data tools that are already out there. And so along the top axis here, I'm going to give you a little bit of information about what's going on in the astronomical community in the last 20 years that has to do with big data and streaming technology. So in 2002 was the foundation of something called the International Virtual Observatory Alliance. So this is this big alliance of different countries that comes together and tries to figure out how can we make astronomical data and tools available to the public for anybody to use across different countries and move data around because the sky is open to everybody. In 2004, the IVOA drafted something called Virtual Observatory Event, or VO Event, which is an alert system that sends out an alert, a message basically, whenever something interesting is being detected on a telescope. So it's basically like a little Twitter feed for a telescope. In 2010, and every about 10 years, the astronomical community puts together something called the Decadal Survey, where we talk to the community and figure out which are the large projects that we want the government to sort of put funding towards, which are the ones that we agree are important for lots of different science projects. And in 2010, the Decadal Survey recommended something called the Large Synoptic Survey Telescope, which is the project that I work on at the University of Washington. And then in 2011, there was an evolution of the IVOA's VO event protocol there. And in 2014, the LSST, the Large Synoptic Survey Telescope, was started, funding was initiated by the National Science Foundation. And we expect that this telescope, it's under construction in Chile right now. I don't have any pictures. I should Google some pictures. It's really cool to see a new telescope being constructed. But that's coming online in the next 5 years or so. But we're putting together all the data pipelines right now. And so you might not think of the night sky as something that is changing all the time. It looks like this thing that you just look up at, and it's there, every day. It kind of looks maybe slightly different. Things are in a different place. But there are things that are changing in the night sky all the time. And so that's why we're building this basically Twitter feed, this news feed, I should say, not just Twitter, a news feed of updates from the night sky. We want to know when supernovae are going off. We want to know when asteroids are moving around. We want to know when there are eclipsing stars that are making stars, dip in brightness, and that kind of thing. So there's all kinds of things that are happening in the night sky. And we want to set up the system such that we can find out about it really fast, within a minute of this happening and being detected on the Large Synoptic Survey Telescope. And we want to get the data out to the public so they can do cool things with it. You could do whatever you want. You could, write an app that turns this all into music, and you could listen to the stream if you wanted to, or something like that. Or we send it out to other telescopes and robotic telescopes so that you could basically do follow-up observations and get spectra and do colors and figure out, what types of objects are these, and be able to better characterize them by collecting more data. And so this is something that came out in the Seattle Times just last week, an article about this new institute at the University of Washington called DIRAC, which stands for DIRAC, Data Intensive Research in Astrophysics and Cosmology. And so one of the things that we're going to be doing with the Large Synoptic Survey Telescope is to track all these asteroids and build up a database of asteroids such that we can we can figure out their orbits, and we can predict whether or not these things are going to come in contact with the Earth, and we want to be able to do something about it. So in 5 years, it says here, a sky scanning telescope, that's the LSST in Chile, will begin hunting the heavens for asteroids on a collision course with the Earth, and scientists like myself at the University of Washington are at the forefront of work to spot them. It's very exciting right now to get involved with astronomical data streams. And so I just had this quote here from Ghostbusters, which I love. Personally, I like the university. They gave us money and facilities. We didn't have to produce anything. You've never been out of college. You don't know what it's like out there. I worked in the private sector. They expect results. So I'm not sure about what it's like at Microsoft. But in academia, we're expecting results too. We're expecting to do great things with the LSST. And we're going to put together basically something that is a valuable service. This is a service to the scientific community so that they can take the data and they can do some really great stuff with it. And so I have to talk about a little bit more about Ghostbusters, of course, if I'm talking about streaming data here. And so I think people, at least in the astronomical community, and maybe not so much at Microsoft, but they're a little bit afraid of streaming data and streaming technology. And that's because streaming is it's more complex, right? You don't do the traditional, batch work, and when you're building up a pipeline, it's very different. And so people get really scared about crossing the streams. Why? Because it would be bad, right? Try to imagine all life as you know it stopping instantaneously and every molecule in your body exploding at the speed of light. It's not that bad, is the point. It's a little bit intimidating to get started, but it doesn't have to be that bad. And so the radical idea here is by the end of the talk, I'm going to hopefully give you enough, just a little bit of tooling so that you can jump in and play with a little ecosystem that's all open source and kind of get ready for astronomical data streams, because we're gonna cross the streams here. So you're gonna endanger us, you're gonna endanger our client, the nice lady who paid us in advance before she became a dog. Not necessarily, there's definitely a very slim chance we'll survive. I love this plan, I'm excited to be a part of it. Let's do it. This job is definitely not worth $11,500 a year in academia. And so the idea here is that we want to sort of change the face of astronomy, okay? We want people, all types of people. We want universal design, basically, in astronomical data streams. We want people here at Microsoft and attending PyData to be able to contribute. We want a system that is going to be really inclusive so that it can be really innovative. Okay, so I'll give you my last slide here, mid-talk. Why is this interesting? Astronomical data streams are open to the public, awaiting creative use. We've made some tech choices with no hard requirements on programming language and a low barrier to entry. We have an ecosystem that has wide support and use cases outside of astronomy, enhancing flexibility, usability, sustainability. What are we looking at? For transport, we're looking at Apache Kafka. Why? Because it's scalable in cluster mode, replicated by design, allows for stream rewind when we make a mistake, and it has many use cases that we can share across our systems. For serialization of data, we're looking at Apache Avro. For fast parsing with structured messages and typing, and strictly enforced schemas, but it allows for schema evolution when the data needs to change. For filtering, we're looking at Apache Spark. Why? Because it has a direct connection to Kafka, and it has a very batch-like stream interface. You can use Python, you can use some SQL-like queries, and basically you can do batch-like analysis using Spark, and so it makes streaming a lot less intimidating. And what can you do? You can deploy, all of what I'm showing you has been Dockerized. So you can deploy this Dockerized mock stream testbed with Kafka here on my GitHub under this alert stream link. And I'm going to show this slide again at the end. You can check out a sample of our Avro schema to see what the data looks like that we're using for astronomy. And you can check out this website where I've made some Dockerized Jupyter notebooks to do a complete how-to that you can deploy alongside the Kafka ecosystem testbed to do filtering with Spark using Kafka and Avro. It's called bilao, which is a Filipino word for a strainer or a winnower. Okay, so this is basically what the design of our system looks like. We are getting data from the telescope, and it's going to go through. We have new data that's collected every 39 seconds on the LSST. It's going to run through our pipelines. We're going to do some detection algorithms on our images to find new sources, things that have changed, things that have moved at some level, about 5 sigma. I think it's 5 sigma level. And then we're going to have a distribution hub, which basically sends out these alert streams to these community brokers. So there are brokers, these large-ish, medium-sized collaborations that are going to be taking the full stream of alerts and then sending them out to subscribers on the other end. So you, as an individual user, you could subscribe to any of these community brokers, which are doing things like adding value. They're doing characterization. They're going to say, this is a supernova, so you can subscribe to these supernovas if you want them. Or if you wanted to, you could get your friends together and you could say, hey, I would like to put together a community broker. Give me this full stream of alerts. And we'll say, sure, here you go. Take all the data that you want. And you can go ahead and you could do that. So you guys could build up and test your algorithms on this public data stream. So what we're trying to do here is we're sending out the alert stream to these community brokers. We're also going to have this alert. Oh, it doesn't show up very well. There's black here that's supposed to show you the flow. Anyway, it goes down. You get the point. It's a stream. It's going down. We're also going to have an alert database. So this is why we're using Kafka, because it's really nice to send all the same data to the community brokers and sync it up with the alert database so we can keep track of all the data that we're sending out. It's very important. This is scientific data. We want to do reproducibility, right? We're really concerned about that kind of thing. And we want to keep all these things in sync. We don't want to lose any data. We're also sending out images, little postage stamp cutouts, we call them, postage stamps, of what these 5 sigma detections look like. They could be, completely round because maybe they're star-like objects, or they could be extended sources. They could be, if they're moving objects or whatever, asteroids and that kind of thing. So you could do image characterization if you wanted on the postage stamps. And then, so the end users are down there. And we want it to be even easy enough that my dog, Tweak, I also have a dachshund, by the way, Tweak can, listen to the stream if she wants to while she's barking. And so these are the large alert streams that are open to the public. There's going to be one that's very similar that I'm also working on at the University of Washington called the Zwicky Transient Facility. And that's coming online next year, actually. So if you want to practice, you could subscribe to that public data stream. We're going to have about 1,000 alerts per visit. So this is 1,000 objects every 45 seconds for ZTF, the Zwicky Transient Facility, and 10,000 every 39 seconds for the LSST, which means that there'll be 1 million alerts per night from ZTF or 10 million from the LSST. The size of each alert is going to be 20 kilobytes for ZTF, 50 to 150 kilobytes for the LSST. And so that means our nightly data stream ends up being around 20 to 40 gigabytes for ZTF, or about a terabyte a night. This is just the alert data, not even the image data. This is just the alerts, basically the text that's being sent out and the numbers that characterize what the alert looks like, and the little postage stamps, a terabyte a night from the LSST. This is going to be very big for astronomy. If you look at a database of all of the VO events to date, this is the one database that we really have from April 2014 to yesterday. There have only been 1.6 million at this VO event database place, which means there's about 1 per minute. And so we're going from 1 per minute to 1,000 every 45 seconds next year, and 10,000 every 39 seconds in 2020. So it's going to be big. So we would welcome help. There's a lot of cool things that can be done here. And so, okay, let's dig a little bit deeper into the ecosystem and how it works and why we made these choices. So again, I said Apache Kafka has scalability, replication, allowing for stream rewind is very important. Apache Avro, structured messages and schemas, and it allows us to send out these postage stamps. You can actually embed images in Avro data format. And then we do all our filtering, or planning to do our filtering, with Apache Spark. And so how does Apache Kafka work? It basically works like a distributed log system or a messaging queue. And they've sort of rebranded and reinvented themselves recently as a distributed streaming platform. And so it's a strongly ordered, basically pub-sub streaming platform where you have these messages and every message has an offset. And you basically have producers that write to these logs, and consumers keep track of, and the system keeps track of where the consumer is by keeping track of the offset where it is in the log. And this way you don't have to have multiple streams per consumer, so it scales really well when you add multiple consumers, which is what we want. We don't want to have one copy of the stream per consumer. This is a terabyte of night that we have to deliver to the public. It's highly scalable. It's used in production in LinkedIn, Netflix, and Microsoft. I forgot that I put that on the slide, but it's used here at Microsoft. It has great clients and connectors, including Python, which I love. I love Python. So it's got good usability. And so there's a little diagram from the Kafka website of a Kafka cluster. It's got databases that you can connect, apps that you can connect. It's really pretty simple to get going, basically, on a Kafka system. So here is what our little streaming testbed looks like if you go to AlertStream. You'll get a Docker Compose file for Kafka and Zookeeper, so you can just spin up the whole system using Docker Compose. It configures a connection to the Kafka broker and sets the stream topic. So this is what you do. You just do from the alert stream, import alert producer. This is if you want to mock a stream of alerts that's sent to Kafka. So in alert producer, you set the topic, the name of the topic. You could say, this is my alert stream. And the schema for the alerts, which is just a JSON schema, and I'll show you an example schema. And then it takes a dictionary that follows that schema, and you can turn Avro encoding on or off. Maybe you just want to use the dict and send the messages like that. You don't want the Avro encoding, so you can turn it on or off. And here, this will just set you up so you have your Kafka system, and it has a stream of alerts all set. And this will give you the actual LSST data. You can also use template consumers to see the alerts that you sent to the Kafka broker. So again, from LSST alert stream, let's see, oh, that's wrong. It's alert consumer there. And from when you set up your stream reader, you just give it also the topic that you want to subscribe to, the name of the stream. So you would say, I want to listen to my alert stream. And you can give it a schema. It can be different, actually, than the one that you produce to, and I'll show you an example of that. And then you just poll the stream reader, and if it has a message, then we say print the message. If not, keep going until you get a message. And you can do also turn stamp collection, the collection of the images. Maybe you don't care about the images. You can turn that on or off, too. And then there's also a script that just monitors the stream to see how many messages there are. So are you familiar with Apache Avro? Are there people that use Avro? Okay, great. There's a few people in the room that use Avro. Avro is really nice because it applies structure to your data, but it allows you to have it outside of a database, basically. So here is just a diagram from Databricks, actually, where unstructured data is sort of your text files and your CSVs, so it's more flexible. You can put whatever you want in there. Then you have semi-structured data like XML or JSON, which allows you a little bit of the structure, and you have headers and keys and that kind of thing. And then you can go to much more structured data, like if you use a SQL database, or if you use Avro or something like Parquet, where you get much more efficient storage and performance because you can put in typing in your data. And the nice thing about Avro and Parquet is that you don't have to have a database, so you can really do bulk transport of large sets of data really easily. And another reason why we use Avro is because the messages in Kafka, they suggest Confluent is the startup company that's really taking care of Kafka in the open source world. They suggest using Avro for their messages, and it's been pretty nice to work with. And so what you do is you define a schema with JSON, and then you can have dynamic typing and strict adherence to the types. Like you could say, this is a byte stream for an image, and this is a float, and this is a long, this is a string. And it's used in production, and it's also used in science. So we use it in astronomy, but also the genomics world also uses Avro. So it's good enough for cancer data. So this is what a sample schema looks like. For example, you have a namespace here, and you have a type. This is a record type of data, and for users. And so you have 3 fields here. You just have the name, which is a string. You have a favorite number, which is an int, or it could be null. And if you have a favorite color, it could be a string or a null. And so then you have your data, which is separate, and you kind of like wrap up the data in the schema. And so your name could be Ben, favorite color is red, and your favorite number, this is a Python, little Python code, so it could be a random integer from 0 to 10 there. So this is just an example of data formatting in Avro. And so with the LSST and ZTF, we're using the same sort of schema, where we basically have an alert ID, which is a long, and you can add some documentation, descriptions in there. Then we have also candidate IDs, because we want to map all these alerts to specific objects. And then you can also include previous detections as arrays of variable length. And then we can put out the cutout images in there as well. And so this is just showing you how you take your schema for the stamps, for example. So this is a stamp record again, and we have 2 fields, just the file name, and then your stamp file name, which is a string, and your stamp data, which is bytes. And then in Python, you just open up the file, and you read it as binary, and then you have your stamp data, and then you can just pop it in there, and you can send out image data as, or any file, actually. You can put it into your Avro data and send it off in alerts. And this is showing you some of the flexibility that you get with Avro. So here, for example, at the top, this could be a long a long bunch of data, basically, and there might be some fields that you don't really care about, but what you can do is you can set a schema that says, okay, I just want the source ID, the time, the filter, the location, called RA and DEC in astronomy, and the signal to noise ratio. And just give me, I'm going to set that schema, and just give me that data. That's all I want. And then at the bottom shows you that's the data that you get. So you just take your schema, and you can cut out some fields, and then you can get the data that you want there. So this is the data flow that we're looking at, basically, where we have a Kafka cluster that's going to send out this full stream of alerts to filter service, and then send many streams, possibly, of filtered alerts back to Kafka. And the filter service will do something with, possibly, where you take the schema and you can cut down the columns, basically, of the data that you want. And we could take queries, basically, in Spark or Python, and that will cut the records that you want. And then take the filtered alerts and then send them out to these community brokers. And so you can get, like a broker for supernova, a broker for eclipsing stars, a broker for asteroids, et cetera. And so one of the things that we want to think about in terms of what data is available in this alert stream system is what sets the look-back time for batch versus stream. When you're making a query, are you going to the database, the record, or are you going to this, like the Twitter stream, basically, of new alerts? And so you want to think about that, because we're going to have 10,000 per second, right, in bursts, possibly. And so when you make a query, how are you figuring out, like, how do you know that you got all the ones that you asked for if your request time is basically, is at the same level as the data stream that's coming in? And so we really want batch and stream to sort of look the same way. You want to be able to use batch functionality in such a way that you can interact with databases and like SQL-like queries in the same way that you can interact with the alert stream. And that's why we're looking at Spark and Spark streaming specifically to pull from this alert stream. And this is just a comparison of some other streaming systems, like I've worked with Apache Storm, for example. And it doesn't integrate with batch as well. And so Apache Spark, and we've heard a lot about Spark, is really nice because it does give you this flexibility in ecosystems. In the tools that I'm providing in the ecosystem in GitHub, everything is Dockerized, so you can just deploy a Dockerized Jupyter notebook that has Spark in the Docker container for you, and so it has all the tools that you need right there. And so you can deploy it in Docker, also EC2, OpenStack, and you can take data sources from a number of places directly. For example, Hadoop, MySQL, you can read Parquet, and you can read from Kafka, which is really nice. You can also read directly Avro data from Spark. So that's really nice that we can interact with basically large storage systems of Avro alerts. So we can build up our database as basically Avro files. And you can search and query over those files of alerts and find, for example, everything in this part of the sky where you're going to be looking at tonight, and you want to know what's interesting up in that part of the sky. You can search over the storage of files, and you can search over the alert stream in the exact same way. And so the way that Spark works in the streaming system is it's basically taking in the data stream, and every new alert basically is going to be sort of like a new row in this unbounded table. And so here is an example of the ecosystem component called bilao, which is a Filipino word meaning a rice winnower. Winnower was already taken in Python, so I had to be a little bit more creative. Bilao is what you see to winnow rice, or as like a food serving tray. So this is what we're using to filter our Kafka alert stream. So what you can do, you just set up the connection using PySpark streaming Kafka, and you create this direct stream. For example, this one is called My Stream. You point it to your Kafka server. You could say auto offset to the smallest, so if you lose connection, you go back to the beginning of what's available, and then you give yourself a group ID, so you can add more nodes to your Spark cluster if you want to. And then you just have this alert, this map function where I take every alert and I just say, I want the ID for this alert. I'm going to throw away all the data. And all you have to do is you define a little function that says return alert ID, and there you go. You can just map all of the alert streams really, really easily. So then at the end, you apply the map function, and then you just print it out, and you start your Spark streaming context. This works in Jupyter Notebook in the Dockerized container with the ecosystem. So you can go ahead and play with it there. This is just basically the same kind of demonstration here, but we're filtering on right ascension, which is one of the location configurations for in astronomy. So it's like, okay, we want to look at every object in the alert stream that has a right ascension greater than 350. So what we're going to do is you can set up your Spark streaming connection to Kafka. You can create the stream that Spark is going to use, and then you can apply the filter, and then you can start the streaming connection there. And then it just prints to the screen. So that's basically all I wanted to say. If you wanted to go online, you're more than welcome to sort of explore the ecosystem, and you'll be hearing more about the data-intensive research in Astrophysics and Cosmology Institute as the LSST comes online. Thanks.
Thank you, Maria. I find this really exciting. There's so much great data out there that's really hard to get hold of, and to be able to get like a really high volume stream of data coming out that's free to access is incredible, and I hope we get to see more of it. So this is really exciting. I've had one question come in through Twitter, and again, we're taking questions through Twitter by priority. If you're in the room, then we'll go to the room if we need to. But we've had one come in. Are you sharing the schemas for this stream with consumers?
The schemas will be available on GitHub. So they're on this slide. Actually, I have a sample of the alert stream We're also sharing them on the LSST and the Zwicky Transient Facilities GitHubs. And as they evolve, they'll still be publicly available so that you can use them as a template and kind of cut down what you want to get out of the stream. So it's all publicly available.
Have you thought about or considered the possibility if the schema has to change in the future?
Yes, we are thinking about that because the schema is already changing as we're trying to figure out what data that we're going to put in. We will have likely set up multiple streams that come out of Kafka. And so you might have version 1 or version 2, et cetera, as we go through and figure out what is the most useful data that people are going to use. Kafka also, I believe, has a schema-like system where they also help keep track and you can grab new schemas. And so we're going to definitely look at that. And if there are people that use that in the room, I'm definitely interested in connecting with you if you are interested also in that kind of stuff.
Yeah, and we've definitely got a lot of smart people in the room who are going to be able to use this data for wonderful and amazing things. What kind of ideas have you had that people might use this data for? I think there's obviously astronomers are going to be interested to know when things are happening, but what about the non-astronomers in the room? What fun can we have with this data?
I think there is, so one of the issues that we have in astronomy is that we know what to look for a lot of things like supernova and for moving objects, but there is a real possibility, and I mean, we will see things that we haven't seen before. And so that is a great way where people can sort of get involved, looking sort of like at anomaly detection and just interesting object detection. And so, and if you have any sort of real interest, maybe not in the astronomical stream component, but in quality of service. As you know, as the telescope survey, it's going to be a 10-year survey, and you know we might have issues with some of the CCDs or something, and so you can definitely help us out with quality, ensuring science quality in all of our data.
Right. We have just lost the projector screen, unfortunately, but what's the best way for someone to get involved in this?
Yeah, so we have a Twitter stream. The LSST has a Twitter stream, and you can follow along there at LSST and at LSST EPO, Education and Public Outreach Office. There's also a forum called Community, community.lsst.org, and there's a lot of interaction and discussion that happens on Community. And you can find out about all of our conferences, which are open to the public as well. So thanks for that question.
Great. Let's thank Maria again. You have your call to action. There's a lot of effort going into making this data stream available, so chat with her, check out any of those resources, find a way to use it. We're going to break for a minute or two, and we'll be back with the next session. Thank you.